Hi, everyone. Welcome to this merge talk between myself and Ted Yoder's work on four-dimensional toric codes with a non-Clifford transversal gate, and Morphing the color code, a work by Michael Vasmer and Aleksander Kubica. I'll be handling the first half of this talk, and Michael Vasmer will be handling the second half of the talk. We'd like to thank the organizers for giving us the opportunity to present these works, and we think this is a great opportunity to show how these works are related and how we really based a lot of our research along one another's works throughout the years. Okay, so I'll be starting with discussing our work on a four-dimensional toric code with a non-Clifford transversal gate. And you can find this work at the following archive and published links here. So we wanted to start this joint talk by doing a little bit of background on the history behind these results and what were the important results that kind of led up to both of our works. And so in order to do this, I wanted to cover a little bit of background work and start off with some fundamental things about fault tolerance. So I'm going to start with quick discussion on what is a transversal gate? What are we searching for? So many of you probably already heard this, but a transversal gate is a logical gate that is implemented in an error correcting code where each of the physical qubits is addressed in parallel. This is very appealing from an experimental point of view because you just need to apply your single qubit pulses or whatever physical implementation you implement to each of the physical qubits, and there's no need to couple different qubits within the code. And these gates are naturally fault tolerant because if you have an error that occurs in your system, well, the gate itself, the physical gate might transform that error, the error will remain localized. And this is kind of the key principle behind fault tolerance is you want correctable errors to remain correctables. And in order for that to happen, you don't want to be spreading errors throughout the system. So if you were coupling different qubits within your code, you could spread this error, which would lead to a logical error. So these are very appealing set of gates, and they're very well studied in the quantum error correction literature. Okay, and in order to understand our results, a key conceptual notion that is important is the Clifford hierarchy. So you can kind of think of the Clifford hierarchy and its different levels as the complexity of a gate. This is a rather loose analogy, but kind of the higher you are in the Clifford hierarchy, you can kind of associate that with more complicated gates that allow you to do more. So the Clifford hierarchy is defined here on the right is the set of unitaries that map under conjugation Pauli's to the previous level of the Clifford hierarchy. So, and it's the first level is defined to be just the Pauli operators. So, and then following this definition, the second level would be unitaries that map Clifford, that map Pauli's to Pauli's. And these are just what are known as the Clifford gates. Of course, the Clifford gates by themselves, they form a group, but they are not sufficient for universal computation. And actually, they are classically efficiently simulatable. And so the nth level, as I said, are unitaries that map Pauli's to the n-1th level. And some popular examples of such gates are the Rn gate, which will probably come up in the second half in Michael's talk, which is defined as follows. And also this multi-controlled C gate. So the CZ gate, for example, is in the second level of the Clifford hierarchy. The control Z gate is in the third level, etc. And today we'll be discussing a gate a code that has a transversal implementation of the controlled Z gate. So that's in the fourth level of the Clifford hierarchy. And an important point to note is that if you have any gate that is in the third or higher level of the Clifford hierarchy plus the Clifford group, you get a universal gate set for quantum computation. Okay. And there's this important notion relating the level of the Clifford hierarchy and spatial locality in quantum error correction, in topological quantum error correcting codes. And this is known as the Bravy-Koenig theorem. And what it says is that if you have a topological quantum error correcting code that's embedded in D spatial dimensions, then you're limited to, if you were just limiting yourself to constant depth or transversal gates, they're going to be limited to the dth level of the Clifford hierarchy. Okay. So some examples is, and you can actually saturate this bound, and that was shown by Hector Baumann. And for example, the d-dimensional color codes have transversal logical gates that are in the dth level of the Clifford hierarchy. So for example, the 2D color code has all the Clifford gates being transversal. So that's the second level of the Clifford hierarchy. The 3D color code has a transversal T gate, but of course it will not have all of the Clifford gates as well, because that would form a universal gate set, and you can't have a universal set of transversal gates by the Easton-Knoll theorem, but you could still have a subset of these gates. So you could, and for example, you have a transversal T gate, which is in the third level. And there's this nice connection between the gates you get in the color code and the gates you'll get in toric codes. And this was shown in this work by Kubica, Yoshida, and Pastavsky, where they showed that you can relate the color codes and the toric codes through a short depth circuit to show that you can get similar logical gates in d-dimensional toric codes. And as Michael will be discussing that in a lot more detail in his second half of the talk, because that's really the kind of, this connection is the fundamental starting point for their results. But here, when I say transversal, I'm noting that's a kind of more general notion of transversal. In reality, it's a short depth, it's a local short depth circuit, which is transversal with respect to multi-qubit partition, so a larger partitioning of the code. But if you wanted to limit yourself to a single qubit partition of the code, things become trickier, and finding gates that are transversal with respect to that single qubit partition in the toric code is more challenging. And this is where this there was this recent result by Mike Vasmer and Dan Brown, who showed that there is an implementation of the 3D toric code that has an explicit transversal control Z gate. So in this implementation of the toric code, your Z logical operators are string-like, while your X logical operators are 2D membranes for all three code blocks. And this is a pictorial representation of the three different code blocks of your code. So there's the kind of the blue code, the red code, and the yellow code. And this represents their X stabilizers, which are volume-like. And the Z stabilizers will be given by the faces. But you notice how there's an asymmetry between the three codes. So two of the codes are similar, the red and blue, but the third code, this yellow code, has weight 6 X stabilizers. And the important algebraic condition that guarantees that, or that is required for a transversal CCZ in this case, is that the X stabilizers of the code from different code blocks must have even mutual overlap. So if you look at pick any one yellow cell, any one blue cell, and any one red cell, you'll see that their mutual overlap will always be 0 or 2 qubits. So in this case, so if you take this first front yellow one, this blue one, and this red one, their intersection are these 2 qubits in here. And you can check that for all sets of single qubit, of single X stabilizers. Okay, so that was kind of our starting point for our work, is that we had this foundation of different works. And we know that there's this connection between dimension and logical gates in the Clifford hierarchy. And so we wanted to search for a 4-dimensional toric code that had a transversal CCCZ gate, because that's in the 4th level of the Clifford hierarchy. And some of you who might be familiar with quantum error correction literature, or just in general, familiar with quantum computation, might know about the 4D toric code. Might ring a bell, because this was a very famous early quantum error correcting code that was shown to have self-correction properties. But in that 4D toric code, you had a symmetry between the X and Z operators. And namely, you had logical operators that were both membrane-like for both X and Z. But if we want to have a transversal 4th level, in the Clifford hierarchy gate, we actually require an asymmetry between the logical operators. And so we want the Z logical operator to be string-like, while the X logical operator will be a 3D hyperplane. So you have this asymmetry in their dimension, and this is required in order to get higher level gates in the Clifford hierarchy. Okay, and so when we wanted to set out a set of requirements that would kind of constrain our search space for looking for these codes, and we wanted, just like in the 2D and 3D toric codes, we wanted Z errors to lead to a pair of X syndrome violations. And of course, we have this requirement that we need the X stabilizers from the 4 code blocks to have even mutual overlap, just like we had in the 3D case. Okay, and it's very useful in order to look at this search is to consider everything in the dual picture. So in this dual picture, well, in the primal lattice in 2D and 3D, the qubits were placed on edges of your tessellation. Here, the qubits are going to be associated with, if there were edges in 4D, then they're going to be associated with 3 cells in the dual lattice. Okay, so they're going to be a volume. You're going to associate qubits, physical qubits, with volumes in this dual lattice. And we're going to label the X stabilizers of 3 of the code blocks by vertices in this dual lattice, and we're going to 3-color the vertices of the dual lattice so that no vertices of the same color share more than just a 3 cell. They can't share an edge or a face. And so, and this requirement that the Z errors lead to a pair of X syndrome violations will impose that every 3 cell will have 2 vertices each of each of the 3 colors. And the second point is the one I mentioned before. 2 vertices of the same color cannot share, will share at most a 3 cell. They can't share an edge or a face. Okay, so this imposes a set of kind of restrictions on our search space. And this is what we're going to be using to look for lattices that satisfy these properties. Okay, so the 4-dimensional lattice that we're going to be looking for should really, in its structure, be composed of octahedra, where we can color the vertices color in this way, so that opposite poles have the same color, but they do, but vertices of the same color don't share an edge or a face. Okay, and a very useful technique for searching for these tessellations is to look at the structure of these Schläfli symbols. So this was a very useful tool, and I'm just going to have a quick aside where I discuss what are these Schläfli symbols. So they're a compact way of expressing polytopes or tessellations. So for example, a Schläfli symbol just of n is an n-sided regular polygon. So this 3 is a triangle, 4 is a square, 6 is a hexagon. An NM Schläfli symbol is a polytope with m n-sided polygons around each vertex. So for example, a 3, 3, around each vertex, you have 3 triangular faces, right? And this just is a tetrahedron. A 3, 4 is, so if you read it from right to left, around each vertex, you have 4 triangles. This is an octahedron. And a 4, 3 is around each vertex, you have 3 squares. And that's a cube. And you notice that if you just invert the ordering of the Schläfli symbol, then you actually get the dual of each other. So the octahedron is the dual to the cube. Okay, and the tetrahedron is self-dual. So if you reverse the order, you get the tetrahedron itself. But an NM Schläfli symbol can also describe a tessellation of 2D space. So again, it's a tessellation with m n-sided polygons around each vertex. So around each vertex, you have 4 squares, and that just gives you the square grid. Or you have this honeycomb lattice around each vertex. You have 3 hexagons, for example. Okay. And so you can build this up to even higher dimensions. So an NMP is that around each edge, you have P objects NM, of NM where NM is defined previously. So a 4, 3, 3 here would describe a hypercube, while a 4, 3, 4 describes a 3-dimensional square grid. Okay, so you can either define 4D polytopes this way or 3D tessellations. And so you can continue this iteration to higher dimensions. So when we're looking for a lattice, what we want is the underlying 3 cells to be these octahedron, 3, 4. So we're going to look for a lattice whose Schläfli symbol is 3, 4, and then A, B, these are going to be integers that we can search over. And it turns out there is one such tessellation of Euclidean space, and that's this octuplex tessellation, which is given by the following Schläfli symbol, 3, 4, 3, 3. Okay, so this is a tessellation of four-dimensional space that is made up of objects 3, 4, 3, which are these hyperdiamonds. So these are the four-dimensional cells that are making up our four-dimensional tessellation. Okay, and these hyperdiamonds themselves are made up of octahedra, right? So if I look at a small subset of the vertices, you see these octahedra clearly. Okay, and because we've constructed this way, this lattice will satisfy all of the requirements that we need for a transversal logical CCZ, because that was kind of the, we imposed these restrictions on the lattice previously to set out our search space, and then we find our logical CCCZ. And you can use the Schläfli symbols to calculate a lot of interesting properties of the code, such as what are the stabilizer weights of the code. So the X stabilizers here are of weight 24. The Z stabilizers, sorry, there's a slight typo here, are all of weight 3. And you can calculate these properties from the Schläfli symbols themselves. The Z stabilizers have a redundancy that allow for a single shot error correction. And I won't go into that here, but you can read the paper for further description of that. And the code is actually, unlike in the 3D case, the code is surprisingly symmetric across all 4 copies of the code. So here you have 3 of the codes are defined by these vertices, and the 4th is actually defined by the 4 cells, but there's a symmetry here that shows that they're all symmetric, which was a rather surprising result. And you might ask, well, what about higher dimensions? And so the kind of natural generalization is that we would like the underlying 4 cells to be these hyperoctahedra, which are given by the Schläfli symbol 334. So we would look for the following form of a tessellation that has the following Schläfli symbol with the degree of freedoms for integers A and B here. But there actually is no in Euclidean space, there is no such tessellation. There's actually only one in hyperbolic space that would satisfy this criteria. So this kind of shows that the search for codes with the properties that we're after that allow for these transversal non-Clifford gates is actually quite constrained and difficult. They're difficult to find with this exact symmetry that we're after. But for a further discussion on higher dimensions and the connection between the color code and the toric code, I'm going to hand it over to Mike now, who's going to really kind of discuss this in some more detail. So I'd like to thank you for your attention, and let's enjoy Mike's talk.
Great. I'd like to thank Thomas for presenting the context of our results and for giving a really nice overview of their useful results on the 4D toric code. And I'd also like to reiterate thanks to the organizers for giving us the opportunity to present this work today. So I'm going to tell you about some work I've done with Alex Kubica, and on what we're calling it morphing the color code. So what's the main idea? What we're going to be thinking about today is we start with a quantum error correcting code C, and we're going to select a small subset of this code, which itself can be interpreted as a small code. So in the picture, this is this B region. And then we're going to run the inverse of the encoding circuit for this B code. Now, this might seem a bit vague at present, but I will give more details in the upcoming slides. But I just want to quickly think about why would we want to do this. So one thing this will do clearly is to reduce the number of physical qubits of C. And this might be a useful thing to do because, in general, qubits are expensive. So needing few of them is better. Also, what it's going to do is it's going to change how you implement the logical gates that you have available in the code C, which might also be useful. And this is how we're going to connect with the work that Thomas just presented. And the third thing that might happen is you can actually simplify the decoding problem for C. and we'll see an example of this. Okay, so the general procedure, which we're calling morphing, is as follows. So we start with a stabilizer code, C, and we're going to select a subset of the physical qubits of C, and we're going to denote the subset by B. Now we can define a new code on B, and this code has stabilizer group, which is generated by the stabilizers of C that are fully supported on the qubits in B. And the key thing here is that the stabilizers of this B code are also stabilizers of C. And this means that the logical operators of C that have support in B are going to act as logical operators of the B code. And this is crucial because it allows us to understand how the logical operators and stabilizers of the code C are transformed by morphing. And as I said, so actually to do this morphing procedure, we just implement the inverse of the encoding circuit for the B code. So this is the general procedure. And the kind of question is, how do we choose these B subsets? And what we're going to be talking about today, what I'm going to tell you about is an example. And well, the example we looked at is the color code. So Thomas has already introduced this code, but I'm just going to give a quick review. So we start with, and this is the definition of the 2D color code, but of course it generalizes to higher dimensions. So we start with a 2-dimensional lattice, which is 3 colorable and trivalent. And 3 colorable here means that each face can be assigned one of 3 colors, such that no 2 faces sharing an edge of the same color, and each vertex is in 3 edges, is what trivalent means. Now we place qubits on the vertices of this lattice, and we're going to associate stabilizers with faces. So, for example, this blue face has a 6-body X term, and the green face had a 6-body Z term. And you know, for each face, we have one X stabilizer generator and one Z stabilizer generator. So what are our subsets going to be for this morphing procedure? So our choice is actually, we're going to choose faces of this color code lattice. Now, this choice is actually inspired, I would say, by a paper by Riga and Terhal concerning something called the 422 concatenated toric code. And you can really think of our results as kind of taking this approach and generalizing it. In the color code context anyway. So we have this face of the lattice, and let's think about what the corresponding code is for this small region. So if we just consider the stabilizers of the big color codes that are fully supported in this small red region, we get 2 stabilizers, which is just a 6-body X and 6-body Z term. And so if you just consider this red region, then the code you have here on these 6 qubits is a 642 code. So 6 physical qubits and 4 logical qubits and distance 2. So we're going to run the inverse of the encoding circuit for this code. And what this is going to do is it's going to replace the physical qubits, the 642 code, with its logical qubits. And we're going to represent this pictorially like this for reasons that hopefully become clear. And the important fact about this morphing procedure is that it doesn't actually introduce any new degrees of freedom. So the number of encoded qubits of the parent code C has not changed. And this morphing procedure allows us to define a whole family of codes, which we call hybrid toric color codes. And this name is because if you can interpret this morphing of a color code face, and you can think about it as transforming this region from the color code to the toric code, and actually in 2D, this would be kind of 2 copies of the toric code. And so in our family, we have these color code, which is just, this picture on the left here. And then we also have the picture on the right, which is which is like toric code like. So you can see that there are no qubits, these gray circles. There are none of these color code qubits left. They've all gone. And we just have these ones on these toric code regions. But then we can get this middle picture where we have kind of combination of color code regions and toric code regions. So now I'm going to connect our work more explicitly to the results presented by Thomas earlier. So the important thing about this morphing procedure is that in the color code context, it's a geometrically local constant depth circuit. So this means that these hybrid toric color codes are going to inherit the fault-tolerant logical gates of the parent color code, but possibly with a different implementation in general. But yeah, the if we have a transversal gate of the color code, for example, this morphing is not going to make it might not preserve its transversality, but it will preserve it up to some kind of a multi-qubit partition. And what we can show is that morphing all the faces of the same color of a d-dimensional color code transforms this into d copies of the d-dimensional toric code. So this really provides an implementation of the result of Kubica, Yoshida, and Pastovsky, which Thomas talked about earlier, about where they showed the existence of circuits that could do this kind of thing, but we give an explicit recipe of how to do this. And so as an interesting example, you could start with a color code which had a transversal control Z gate. And then if you apply the morphing, as I described above, you'd end up with 4 toric codes with the fault-tolerant control Z gate. And furthermore, if you make a specific choice of lattice for the color code, you can recover 4 toric codes with the transversal control Z gate. And these are exactly the same codes that were presented in the previous talk. And I mean, understanding kind of Thomas and Ted's result and these connections between the color code and toric codes and transversal gates is really a big inspiration for this work. Okay, so changing track slightly, there's an interesting question we thought about once we had this family was, okay, we've got this family, but how can we decode them? Because these codes are kind of strange. They have regions of the toric code, regions of the color code, but how can you decode them? And the nice thing is, so we managed to develop an algorithm to solve this decoding problem. And really this algorithm, it works for the whole family, but in the special cases of the toric code, it recovers this minimum weight perfect matching decoder. And for the color code, it recovers the restriction decoder. And we think this approach would generalize to higher dimensions, but we only really considered 2 dimensions in this work. So I'm just going to present you the result of some numerics here. So what this plot is showing you, I'm plotting the error threshold, P sub C, against the unencoding probability. And just to describe what this unencoding probability is what we did is we generated random hybrid toric color codes. And what we wanted to do is kind of vary the average number of morphed regions. So the unencoding probability is telling you something about the average proportion of morphed faces. So for example, at this point of Q equals 0, we're having, you just get the color code, and then at Q equals 1 up here, we're getting some kind of toric code, but actually these toric codes will be kind of on random tessellation subject to some kind of constraints. And then in the middle here, like at Q equals 0.4 or something, you'd get these hybrid codes. And what you can see here is that, the threshold, so we recover the threshold kind of previous results for the color code at the 0 and for the toric code at the 1. And each of these points, we do this kind of standard threshold analysis so we're considering an error model where there's only phase flip errors, no measurement errors, and we just plot the logical failure rate against the Z error rate, and we, for different sizes of code, and we do the kind of standard finite size scaling analysis to estimate the threshold. And this is enough to establish the threshold for the family, because as these codes are CSS codes, we can correct X and Z errors independently. So what we're showing you here is that the decoder seems to perform well across the whole family, and sort of as you get closer to the toric code, the decoding problem is becoming easier, so the threshold is increasing. Okay, so the final example I want to tell you about is what I think is a very nice example of a hybrid toric color code. So we can make a family of these such codes, and we can build them from the d-dimensional Reed-Muller code. So just as an example, there's this reasonably famous 1513 Reed-Muller code, which can itself be understood as a color code. So this has actually already been shown in Thomas's talk as well, but I'll recap the definition of this code. So we have qubits on the vertices, and then we have X stabilizers associated with the cells. So here there are 4 cells, 1 red, blue, green, and 1 yellow. And then the Z stabilizer associated with the faces. Now this code is the reason people like this code is it has a transversal logical T gate, which, as Thomas mentioned, is necessary if you want to get this plus the Clifford group gives you universal computation. And this is also the R3 gate in the notation of the previous talk. So what we're going to do is we're just going to morph, for example, this top yellow cell. And if you think about this top yellow cell, it's got 8 vertices. It's actually a cube, and the code that you kind of get when you just consider the restriction, the stabilizer group to this cell is an 832 code. And so when we do the morphing, we map these 8 physical qubits here to 3. So, we lose these, and we're getting these 3 qubits, which are shown here in the center of the faces. So we've gone from a 1513 code to a 1012 code. So we've reduced the number of physical qubits by 5, and we've also reduced the distance by 1. So the code is now just an error detecting code. And I'm just showing you here how some of the stabilizers that you get, and you can compute how these, it's easy to see how these transform, because you can just, you just consider how the stabilizers act on the logical qubits of the 832 code, and then it's simple to work out what they look at, what the stabilizers look like in this code. And why is this code nice? So this code has a fault-tolerant logical T-gate. So I'm showing you the implementation here. So on the kind of qubits that you had from the original color code, you do T in, T dagger. And then on these 3 new qubits, we're doing this CCZ gate. And you might think, like, why is this seems a bit suspect, as we're doing this entangling gate here. And this could definitely spread errors. So it could spread a weight 1x error to that error times a weight 2z, for example. And this might be bad, but the thing is that these errors can only propagate, any detectable error will propagate to a detectable error. So it's still fault tolerant, because we can still detect the error even after we've applied this entangling gate. So this code is actually the smallest example of a family of codes with this kind of structure. And so you can learn more about that in Alex's talk, and there's an upcoming paper by Iverson and Kubica about this as well. And so we like this code because it's the smallest code to our knowledge which has a fault-tolerant logical T-gate. And what we did is we looked at this code in the context of magic state distillation. So very quickly, magic state distillation is a protocol for distilling high fidelity magic states from lower fidelity input magic states. And these magic states are used to implement non-Clifford gates in, for example, a 2D surface code. So it's coming up with these protocols is an important topic in fault tolerance. And what we did is we compared our 1012 code with this 1513 code. And in this plot here, you can see we did the kind of standard magic state distillation analysis. So you have some input error on your magic states, and you are interested in what's the kind of output error you expect on your output magic state. And so this green line is showing you the kind of break-even point where you might as well just retain the input ones. But once you're below this line, you're suppressing the errors on the input magic states and getting a higher quality one out. And you can see there's this region where our 1012 code, this blue line, is below the green line and the orange line. So we're getting improved performance. And the 1513 code does end up winning eventually, and you'd expect this because it has higher distance. But I think the interesting thing about this is not necessarily this protocol, but what this represents is an actually new type of protocol, because it uses 2 different types of input magic state, CCZ and T, whereas previous protocols only use 1 type. Okay, so today I've told you a bit about this general procedure for morphing codes, and we've studied the special case of the color code. And this allowed us to define a family of hybrid codes, which the family contains both color code and the toric code. We looked at the construction of these hybrid codes and their fault-tolerant non-Clifford gates, and this is how we made a connection to previous results about transversal gates in toric codes. And we also looked at how you can decode these codes. And I think what I really want to emphasize here is that this idea of morphing, I think, is more general than the color code, and I think it might be quite interesting to apply it to other families of codes, and possibly it might lead to interesting new magic state distillation protocols and other things. So yeah, thank you all for listening.